Good day, students. Welcome to our another online session for the course Computer Organization, and we are covering chapter number 5 of the book while dealing with hierarchical memory system. In our previous session, we've discussed about the importance of the hierarchical memory, and we've discussed about the different types of the memory modules that have been used in the computer system, and what are their benefits and what are their limitations. And then we've discussed about the cache memory in detail. Also we've discussed the principle of locality, and we've seen that if you have to find a block in a cache memory, then how we're gonna know that that block exists in a cache memory or not. We've discussed that that is totally dependent upon the orientation of the cache memory, as cache memory has been divided into three subcategories. Either the cache memory can be directly mapped, or the fully associative or set associative. And we've discussed about how we're going to identify a block in a direct map cache with an example. And we've seen that we've got a block identification strategy. Basically, as block address is been distributed into three different categories: the tag bits and the index bits and the offset bits. And then in today's session we will be looking at how that address has been subdivided, how a hit NMS is being generated in a cache memory. So we're assuming a direct memory, and in this particular example, let us see the specification of this memory first. So we've got the cache memory with a total location of 1023, or we can say that 1024 locations total, and the address is distributed from 0 to 1023 to 3 location. And we've got the address that is generated by the processor, that is of 32 bits. Block address is 32 bits. Now we're going to see how we're going to identify the index bits and the tag bits, as index bits are directly associated with the number of locations in the cache. So since we've got 1023 bits, so we require 10 number of bits in order to set for the index bits. So index bits are 10, as we've got the number of bits equals to 1024. So the basic formula which we use to identify the index bit is basically that is equal to 2 raised power index, where 2 raised power index sets the total number of locations in a cache. Basically, that is equal to total number of locations in a cache. That is equal to cache size divided by block size multiplied by the level of associativity multiplied by set associativity level, where for the direct map cache can be seen as a one-way set associative cache. So as the locations are given here, 2 raised power index equals 1024, which means that index is equal to 10 bits, equals to 10 bits. And the remaining bits are basically the tag bits, while the byte offset or the block offset is dependent upon the number of blocks you can store in a single location. So that depends upon that configuration. So we require the index bits and tag bits. First of all, for any block address, what we used to do is we take the index bits and access the location in the cache memory by those index bits. Then the next thing is to generate the hit NMS. The next step is to compare the tags and the valid bit. First of all, we compare that store tag, which already, if there is a block in a cache memory, we compare that tag that has been stored at that particular location with the tag that is being originated in the block address. If the tag matches with the stored tag, then this comparator, basically this is a comparator, this comparator will produce This is a comparator and it will produce 1 at the output for the tag match. The next thing is we're gonna see that the data was valid or not, and we're gonna see the valid bit. So this is the valid bit. We're gonna see that, and if data is also valid and tag matches, then it produces a hit, and otherwise it produces a miss. And if hit was generated, then we access that location and move the data to the data bus. Okay, so this is the way we identify a block in a cache memory. We identify hits and miss, and we move the data towards the processor from the processor, or from the processor towards the cache memory, or towards the RAM. Right? Now coming to the larger block sizes, if the block sizes are larger, for example, we've got total number of blocks in a cache memory that are 64, and 16 bytes per block we can store that. So how we're going to identify that the block number 1200 maps to which location in the cache, as cache only holds 64 blocks. So for the 64 blocks, the index bits are basically 6 bits, because 2 raised to power 6 equals 64, 2 raised to power 6 equals 64. The offset bits are dependent upon the total number of locations in a block, or total number of bytes in a block. Since we've got 16 bytes in a block, so 16 bytes can be represented by 4 bits. So we require 4 bits to identify which byte is required by the processor. So these 4 bits are the offset bits, then 6 bits are the index bits, and the remaining bits are the tag bits. Now let us see for which block number or the block address maps to which location. So what we used to do is we used to divide that block number with the total number of bytes in a block. So 1200 divided by 16, and we will take the remainder, or the float value, the remainder value. So that is basically 75. So block number 75. So next thing is we have to know that that particular block maps to which location. So what we used to do is we used to take the mod of the block address with the total number of locations in the cache memory, and the resultant is the location in which we store that particular block. So 1200, the address basically maps to the 75th block, and 75th blocks maps to the 11th location in the cache memory. Now, what are the block size considerations? Can we assume a smaller block size that would be beneficial, or can the larger block size are more beneficial? So the larger block size definitely will reduce the miss rate due to the spatial locality concept. But in a fixed cache size, larger blocks would have the fewer number of times in the cache memory. So more competition is involved in order to move in and out from the cache memory. So in that particular scenario, it will not gonna help but increase the miss rates. So the larger block size will definitely pollute our cache memory with irrelevant data. So uh, replacement would be intensive, and it will not gonna help us. So we have the larger miss penalty rates in that particular scenario, as we can override benefit of reduced miss rate with that. So early restart or critical word first can help. These are the schemes which we will study later on. Now coming to the cache miss. So if you've got a cache hit, CPU normally gets the data, required data in a normal way. But if the cache is missed, so what we have to do is, first of all, we have to stall the CPU pipeline. We have to wait for the data, and we have to fetch that block from the next level of hierarchy. That in our case, that is RAM. And in case of instruction cache miss, normally our machine code resides in the instruction cache. So we have to restart the instruction fetch. But for the data cache miss, and we have to have the complete data access again. Now coming to the scenario in which processor works on some particular block, and processor want to update that block, since we know that that block exists in the multiple levels in the memory. So where to update that block, that is dependent upon the strategy that we use in order to update the block. The first strategy is the write through strategy. Write through strategy is a simple strategy and it allows us to update the blocks in a cache memory as well as in RAM at the same time. So we can see the scenario that we've got a CPU here. CPU works on some particular block. CPU has the updated copy, cache has not the old copy. Cache is represented by $sign, and RAM also has the old copy of that particular block. So write through strategy tells us that we would update the cache memory and RAM at the same time. So the benefit of write through strategy is that we've got the data consistency here. So the data is consistent, but the drawback is since we have to update the RAM and RAM is a slower device, so this scheme is a bit slower and processor would suffer in terms of latency and wastage of clock cycles, as we have to access RAM again and again for each for each data write. So in terms of data consistency, this is good, but in terms of access rates and latency, this strategy is not proving fruitful. So one data write hit could just update the block in cache memory, but then cache and memory would be inconsistent. So what writes through strategies do, it's update the memory at the same time, but makes write take longer, because we've discussed that the RAMs are the slower devices and we have to access the RAM, so we have to suffer in terms of clock cycle time. So the solution is we can use a write buffer in between the cache memory on the CPU or between the cache memory and the RAM. So we would update those buffers and we hold the data waiting to be written to memory with the buffer. So CPU continues its processing immediately without waiting for the data to be written to the memory. One thing that is problematic, that if the buffer gets full, then definitely we have to stall the pipeline and we cannot write further into the cache memory of the RAM. The next strategy is write back strategy, and in write back strategy it says that we would only update the cache memory, and if there is a block replacement request, then when the block is replaced, then we would update the RAM memory. So in this particular way, we don't have to access the main memory each time for every write, but in that case, the cache memory only holds the updated data, while the RAM can still hold the previous one. So data consistency is the big concern here. So data is not consistent. So what we could do is we could write it back to memory, and we could use the write buffer tool or replacing blocks to be read first. By the dirty block means that there was a block and there was some processing done on the block, so any modified block is considered to be a dirty block. The next strategy is a write allocation strategy. So what would happen on a write miss? So in that particular scenario, this is there are alternatives for the write through. So we could allocate on miss, fetch the block, and with write allocate, what we used to do is we used to move that block in the cache memory first to the upper level, so that that block can be accessed by the processor. Whereas for the write around strategy, we don't fetch the block, since programs often write a whole block before reading it. There was examples. I'm just skipping some of the slides. Now, how it would measure the CPU performance, as there is a memory element also introduced in, and now the CPU time is not only dependent upon instruction count and CPI, but also the memory stall cycles that are produced in terms of accessing the memory. So their contribution is also there. Now the execution time is dependent upon the behavior of the memory as well. Well, this was all for today's session. In the next session, we start from this slide and we will discuss about how this performance has been uh, affected by the stall cycles in the cache or the memory.